Our new unit is on acids, bases, and pH. Let's take a moment now and go through some of the basis and the foundation for acids and bases and the pH scale. The basis of the acid-base relationship and the pH scale is from the autoionization reaction that takes place in water. In water, a small amount of the water molecules autoionize to make hydronium and hydroxide ions. This takes place in all water. A small fraction of the water will self-ionize to make hydronium and hydroxide ions. Chemically, hydronium is the same thing as H+ ions. They're essentially synonyms of one another. They represent the same thing chemically, whether it's written H+ or H3O+. Because this is an equilibrium system, the water has an equilibrium constant, referred as K sub W, where the W represents water. As we've seen in previous equilibria, the equilibrium constant is equal to the products divided by the reactants. In this case, because the reactants are in the liquid phase, they drop out of the expression, leaving us with Kw as 1 times 10 to the negative 14th, which is equal to the hydronium concentration times the hydroxide concentration. If we look at the autoionization reaction for water, the hydronium and hydroxide form in a 1-to-1 ratio. Consequently, in pure water, we find that the H3O+, the hydronium concentration, is equal to the OH-. In this circumstance, we say that the solution is neutral, and the solution would have a pH equal to 7. Solving for the hydronium and hydroxide concentration, we find that the hydronium is 1 times 10 to the negative 7th molar, which is equal to hydroxide as 1 times 10 to the negative 7th molar, and this is characteristic of a neutral solution, and the pH is 7. If we have a solution, initially it's just pure water, we have the equilibrium, the self-ionization of water taking place. The hydronium and hydroxide concentrations are equal. Let's say we add something to this, such as hydrochloric acid. Hydrochloric acid dissociates 100% into H+ ions and Cl- ions in water. The H+ ion is the same thing as a hydronium ion when it's in the water. What this is going to do is cause the hydronium concentration in the water to go up. Now, from previous experience with equilibria, if the hydronium concentration goes up, that's going to cause the water reaction to shift to the left, and consequently the hydroxide concentration is going to go down. This would need to be true, and if you look at it mathematically, if the hydronium concentration gets bigger, the hydroxide concentration has to get smaller so that the hydronium times the hydroxide will still equal the water constant, which remains at 1 times 10 to the negative 14th. In this circumstance, where the hydronium is now greater than the hydroxide, this would be a solution we would characterize as being acidic, and the pH of this solution is going to end up being something less than 7. This would be some of the identifying traits or features of an acidic solution. When the hydronium is greater than hydroxide, that makes something acidic. We have a pH less than 7. Let's change to the example where we put something such as sodium hydroxide into water. In water, sodium hydroxide, being a strong base, dissociates 100%, creating sodium ions and hydroxides in the water. This causes the hydroxide concentration to go up. Now again, as the hydroxide concentration goes up, the equilibrium shifts left, making the hydronium go down. Mathematically, when the hydroxide gets bigger, the H3O+ has to get smaller so that multiplied together they'll still equal the water constant. In this situation, where the hydronium concentration has now become less than and smaller than the hydroxide concentration, this would identify a solution as what we would say is a basic solution. In this case, the pH is going to be something greater than 7 when a solution is basic. There's several key things we'll need to know for acids, bases, and pH. One of them is the reaction for the autoionization of water, where water ionizes, self-ionizes into hydronium and hydroxide ions. A second is the equilibrium constant for water, which is 1 times 10 to the negative 14th, which will always be equal to the hydronium concentration times the hydroxide concentration for any aqueous system at room temperature. A third is the relationship for calculating pH. pH is equal to the negative log of the H3O or hydronium concentration. Similarly, something known as the POH is, the POH is the negative log of the hydroxide concentration. Another key relationship is that pH plus POH will always add up to equal 14. And then lastly, we have the three relationships with H3O plus and OH minus. If H3O plus is equal to OH minus, the solution is neutral. pH is 7. H3O plus greater than OH minus, it's acidic. We have a pH less than 7. And if the H3O plus ends up less than the OH minus, we have a solution that's basic, and our pH will be greater than 7. In this first example calculation, we're provided that the H3O plus concentration is 0.025 molar. We also know the pH equation, which is pH's negative log of hydronium concentration. We can insert the 0.025 molar for the hydronium concentration and use this to calculate the pH. And we find the pH of the solution is 1.60. The next part, to get the OH minus, we have the relationship that Kw, which is 1 times 10 to the negative 14th, is always equal to the hydronium times the hydroxide concentration. We can insert the hydronium concentration and calculate the hydroxide. Solving for the hydroxide, we get that the hydroxide concentration is 4 times 10 to the negative 13th mole. To calculate the POH, we have a couple different strategies that we can utilize. One, we can use the relationship that pH plus POH always add up to equal 14. Solving for the POH, we get that POH is equal to 12.4. A second strategy is use that POH is negative log of the OH minus concentration. Placing in the hydroxide concentration, we can now readily calculate the POH. Again, getting that the POH is 12.4 for this particular solution. This problem is similar except in reverse. In this one, we're provided the pH and we want to find what the hydronium concentration is. Again, we can use the pH equation. We take our given pH of 3.2, put that in for the pH, and set that equal to the negative log of the hydronium concentration. Our first step mathematically is to bring the negative to the other side of the equal, so that we now have negative 3.2 equals the log of H3O plus. To remove the logarithm, we need to take the anti-log of negative 3.2, and that'll give us the hydronium concentration. Finishing the calculation, we find the hydronium concentration is 6.31 times 10 to the negative 4th molar. Now that we know our hydronium concentration, we can readily calculate the hydroxide concentration. Because again, the water constant, 1 times 10 to the negative 14th, always is equal to the hydronium times the hydroxide concentrations. We can take our hydronium concentration, insert it for the hydronium, and solve for the hydroxide. Solving for the hydroxide concentration, we find the hydroxide to be 1.58 times 10 to the negative 11th molar. We can now solve for the POH using, again, two separate strategies. Picking one or the other, both will work fine. One can be the pH plus POH equals 14 relationship, or the other strategy would be the POH as a negative log of OH minus concentration. Using either strategy, we end up with a POH of 10.8. Same thing when we use the POH as a negative log of the hydroxide concentration, we get a POH of 10.8. The next problem, we're given the concentration of a weak acid solution and asked to find what the pH of this solution is. We know this is a weak acid because HClO, hypochlorous acid, is not on our list of strong acids, and also we're given a Ka value. Ka values are only associated with weak acids because weak acids are equilibrium systems. Strong acids, on the other hand, are non-equilibrium systems. Only equilibrium systems would have an equilibrium constant associated with them. The Ka, what this stands for, the Ka is our equilibrium constant. the subscript A means that this is for a weak acid. Now fine, all-star chemists, to solve this we're going to use the Rice strategy which we've used for other equilibrium type of problems. The weak acid, aqueous weak acid molecules of HClO are going to go through a reaction in water referred to as hydrolysis. Hydrolysis just means reaction with water. The aqueous weak acid molecules will go through this reaction, producing aqueous hypochlorite ions, and then the water molecules will take a fraction of the H's off of the hypochlorous acid to generate some hydronium ions. This will cause the hydronium concentration in water to go up, making it so the hydronium is greater than the hydroxide in water, and the solution ends up becoming then acidic. Setting up our Rice strategy, the 0.50 molar solution of hypochlorous acid, that's the initial concentration of the acid before the system reaches equilibrium. Initially there's 0 of the hypochlorite ion and 0 of hydronium contributed by the dissociation of the hypochlorous acid. The hypochlorite concentration will go up by some quantity X, and because this is a 1-to-1 ratio, the hydronium ion concentration will also go up by X. Simultaneously, the hypochlorous acid concentration will go down by X. What we now know is our equilibrium concentration of the hypochlorous acid is 0.50 minus X. The hypochlorite ions and hydronium ions are represented by X. Setting up the equilibrium constant expression, we have 2.8 times 10 to the negative 8 is our products divided by our reactants. Now we're going to take an approach here to help make life a little simpler mathematically. If we look at our Ka value, we see that this number is very tiny. Consequently, our numerator, or the amount of product, is going to be very small, and the denominator, the amount of reactants, is going to be a fairly big number. That means the size of X in our equation is very tiny. What this means is, because our X is so tiny, is that when we take a tiny number and subtract it from 0.50, it leaves us with essentially 0.50 when we round the number off. So mathematically, because our X is so tiny, we can eliminate the X from our equilibrium line underneath the hypochlorous acid, giving us our equilibrium quantities for each of our chemicals, which we can now readily insert into the equilibrium constant equation and calculate for X, which will give us the hydronium concentration. We now have X times X over 0.50. Solving for X will give us the hydronium concentration. Solving for X, we get the hydronium concentration to be 1 times 10 to the negative 4th molar. Solving for the H3O plus gives us 1.18 times 10 to the negative 5th molar for our hydronium concentration. Our pH is the negative log of the hydronium concentration. We now know the hydronium to plug into this equation, and we find that we get a pH of about 3.93 for this solution of hypochlorous acid. This problem is similar to the last one, except slightly different in that this time we're given the pH of our weak acid solution. We want to figure out what the Ka value is for the acid. We know this is a weak acid because HCN is not on our list of strong acids that we have. Again, we're going to use the Rice strategy. Our first step is to write the hydrolysis reaction for the weak acid with water. Keeping in mind an acid, by definition, is something that's a proton donor, where a proton is an H plus ion. What's going to happen is our weak acid is going to get rid of the H plus ion and donate that to the water molecule. This creates cyanide 1 minus aqueous ions and turns the water from H2O into H3O plus hydronium ions as part of our hydrolysis reaction. We're given the initial concentration of our HCN solution is 1 molar. That goes in for initial. Initially, we have 0 cyan and a hydronium concentration before the acid reaches equilibrium. Because we're provided with a pH for this problem, our size of our change of the hydronium is not X, but it's actually a known quantity. We have to take the pH of the solution and use that to calculate the hydronium concentration. We can place our pH into the pH equation. So we have 4.62 is negative log of the hydronium concentration. Solving for the H3O plus, we have the anti-log of negative 4.62 will give us our hydronium concentration. Solving for the hydronium, we get the hydronium concentration as 2.4 times 10 to the negative fifth molar. Now that we know the hydronium concentration is 2.40 times 10 to the negative fifth, that gives us the size of our change in our equilibrium. And because our hydronium and the cyanide ions form in a 1-to-1 ratio, that also gives us the size of our cyanide ion change and the size of our change for our hydrocyanic acid. That's going to go down by 2.40 times 10 to the negative fifth molar. We now have the size of our equilibrium line for each chemical. The hydrocyanic acid is 1 minus 2.40 times 10 to the minus fifth, and both the cyanide and hydronium concentrations are 2.40 times 10 to the negative fifth. We can readily put these into our Ka expression for the reaction, and that'll allow us to solve for the Ka value. Our equilibrium constant expression, or Ka, is the cyanide times hydronium concentration divided by the equilibrium concentration of HCN. Since we know our equilibrium values, we can readily plug these in. This will allow us to solve for the Ka value for this weak acid, HCN or hydrocyanic acid. Solving for our Ka, we get 5.76 times 10 to the negative 10 for our value of our equilibrium constant for this weak acid. Our next one is for a strong acid. A strong acid's a bit different because strong acids dissociate 100%. With a strong acid, the arrow that we write for the reaction is not an equilibrium arrow, but rather it's a one-direction arrow because strong acids dissociate 100%, and the reaction proceeds only in the forward direction. Consequently, if we're given that the acid concentration is 0.10 molar, 100% of that turns into hydronium ions. So if we know for a strong acid that its concentration is 0.10 molar, that also gives us the hydronium concentration. So what we have is, therefore, the hydronium concentration is the same as the strong acid concentration. So in a strong acid, if we know that in this case the HCl is 0.10 molar, then the hydronium concentration is also 0.10 molar because all of the acid turns into hydronium ions. We can now use our pH equation, where pH is the negative log of hydronium. Our pH is negative log of 0.10. And for this solution, we find that our pH is equal to 1 for a 0.10 molar solution of hydrochloric acid.